Alright, this is part 2 of the Quizstar review, so let's take a look. Titration curve shows the titration of a weak base with a strong acid. Where is the buffer region? Well, the buffer region is going to be represented by the region right here. That's when you first start a titration, the flat area. In this case, this happens to be a weak base because we're starting at a pH below 12, but it's up there. We're titrating with an acid. The buffer region is going to be right in that area right there, so B Roman numeral 2. Halfway to equivalence, you know, on a weak base, POH is equal to PKB, and then the equivalence point, if you notice, on a weak base titration is going to be below 7. That would be a key thing that would help you on the test as well tomorrow. Next one, titration curve shown below represents a weak base with a strong acid. Which point represents equivalence point? The equivalence point, if you trace this all together, looks like this. Equivalence point is going to be in the middle of the vertical area. So we're really talking about Roman numeral 3 is going to be your equivalence point. We know when you titrate a weak base, so if you titrate NH3 plus with, let's say, H plus, you're going to get NH4 plus. A positive ion is going to act as a conjugate acid, so the pH at equivalence has to be below 7. Next one, which substance dissolved in pure water will it be acidic, neutral, or basic? This is just hydrolysis. So if I have NaCN, I cancel this because that is a heartbreaker. It leaves me with Cn minus. A negative ion will act as a base. Therefore, the solution will be basic. That's your answer right there for 13. Which of the following statements is correct? Well, when we're talking about acid strength, HCl is a stronger acid than HF because Cl has a longer radius. That is actually true because when you talk about binary acids, as you go down from HF to HCl, HBr, HI, as you go to this way, as radius increases, the H snaps off easier. So HF being a small bond, maybe a little bigger than that, like that, the bond is easier to break. Where you talk about are harder to break because it's smaller, the closer the bonds are. Whereas if you take HI, H, and the ion I, when you make an HI acid, the distance, since it's a longer bond, it's actually easier to snap when you start talking. So that's true. Reason why HCl is a stronger acid than HF is the HCl bond is weaker. That is true. The Cl bond snaps off easier because the ions are larger that put it together, or the Cl. One reason why HCl is stronger is that Cl is more electronegative. That is incorrect. That is the answer that you want because it's asking you for the incorrect statement. So C is incorrect. Acids HBr and HI appear equally strong in water. They're both strong acids, so you can't really tell the difference as far as that goes. So the correct answer is HCl is a stronger acid. Doesn't have to do with electronegativity because fluorine is actually more electronegative. Has to do with the bond length. The longer the bond in a binary acid, the stronger the acid. That was, what was that, 14? 15. 15 is a titration problem. When I look, they tell me that it is a titration problem. The first thing I see is I cancel the heartbreakers. Cl cancels, Na cancels, which leaves me with H plus and OH minus are going to produce water. So it's a strong acid, strong base titration. My first step, I know I have to do a vacuum table, is going to be M times L, M times L. I'm going to get moles of the acid and moles of the base. So I start out by taking 0.19 and 0.7, because it's 700 milliliters of HCl. I am going to get 0.13 for my H plus. Then I'm going to take 300 milliliters, or 0.3 times 0.52, is going to give me 0.16 for my OH concentration. If I look at my snorkel box, the first thing I realize is that I am past equivalence. I am past equivalence because I'm adding more OH than H plus. So then that means my 0.13 is going to be my limiting reactant, minus 0.13, minus 0.13, and then on the other side I'm getting water, so who cares? So then when I go down to the bottom, I know that 0.13 minus 0.13, the concentration of H plus is going to be 0. If I take 0.16 minus 0.13, I end up with 0.030 moles of OH left, because that's my excess in my titration. So all I'm going to do at that point then is take 0.030, that's how many moles. Remember, to get molarity, I always need the new volume. Well, I have 300 milliliters and 700 milliliters. which is going to give me the total of 1,000 milliliters, or I'm going to divide by, so if I go here, I'm going to divide by 1 liter. Ultimately, my concentration of OH minus is 0.030. So that's my concentration of OH. If I take the negative log of that, and then subtract it from 14, I get my pH is 12.48. Remember, they're asking me in the question, they want to know what my H plus concentration is. They want to know what's the concentration of H plus. Once I get my pH, like in pH land, all I have to do is remember 10 to the negative 12.48 will tell me what my H plus concentration is. When I did it, this number's a little off as far as rounding. That's the number you should come up with. It's 3.3 times 10 to the negative 13. First thing I do is when I read the problem, I realize it's a titration because it's an acid and a base. So since it's a titration, I cancel the heartbreakers. That means I have H plus, OH minus. Second thing I'm always going to do is I'm going to do M times L, get my snorkel box, figure out where I'm at, do my calculations, and then figure out what they're asking me to solve for that problem. So there's that problem right there. Next one, which of the following is a conjugate acid-base pair? Conjugate acid-base pair, the difference is a single H between them. So if you look right here, this represents a conjugate acid-base pair because I have NH4 plus and NH3. That is a conjugate acid-base pair simply because that has 4 H's, that has 3. The other atoms in the molecule are exactly the same. So that's the definition of a conjugate acid-base pair. Which of the following does not represent a conjugate acid-base pair? Well, difference between them is a single H. Difference between those two is a single H, and then if I look at this one, if I have HCN and NH3, that has a carbon, that doesn't. That means that would not be, plus the number of H's as well. The difference can only be one single H. That's why D is your correct answer for that one. Calculate the pH of a 2.0 times 10 to the negative 8 solution of HNO3. If I cancel that, it means I have basically H plus. It's a strong acid. One of the problems is the value 2.0 times 10 to the negative 8. Remember the H plus concentration in water is 1.0 times 10 to the negative 7. The molarity of this acid is too small. But if you have a strong acid on the test tomorrow, all I would do is take the negative log of 2.0 times 10 to the negative 8. So all I would do is take 2.0, 10 to the negative 8, take the log, boom, and it comes out as 7 point, on that one I get 7.70. That doesn't make sense though, because that's the pH of a base. So the problem is the testing program, when it generated this, the number's bad. So I would, if I gave you something like 0.025, that's what you should be in. It's a strong acid, you would just take the negative log of it. So if I took 0.025, so I go 0.025, log, sign change, the pH of that is going to be 1.60. That's what I would expect you to do tomorrow. The problem is with the initial molarity on that one was way too small. It's actually ridiculous. Next one. 50 milliliters NaOH is added to 30 milliliters of 0.2 C2H3O2. What is the pH of the solution? Okay, so this is basically a titration. I cancel this out. I know that I have a weak acid and OH. So my first thing is I'm going to write the equation. HC2H3O2 plus OH minus, arrow, what am I going to get? I am going to get water and plus C2H3O2 minus, and then I'm going to do my vacuum table. So when I go to do a vacuum table, my first step is I need to find moles of each. So moles of the acid, 0.030 times 0.20, I'm going to get 0.0060. That's going to be my moles of my acid. Moles of my base, 0.015 liters times 0.1. I'm going to end up with 0.0015. According to my snorkel box, I am before equivalence. So my first step is I'm going to subtract 0.0015 minus 0.0015 plus 0.0015 right there. Then this is going to be 0. This is going to be 0.0045. 0.0015, and then what am I going to do? I am going to do this. I'm going to find my new molarity. So 15 plus 30 gives me 45. So I'm going to go down here and I'm going to divide this, and So ultimately, when I divide by 0.045, my molarity of my acid is 0.10. My molarity of my salt, 0.0015 divided by 0.045, I'm going to get 0.033. Now at this point, I know I have to Hasselhoff it. So pH is equal to pKa plus the log of the acid. Here's my acid. It's going to go on the bottom. So I'm going to get 0.10, 0.033 goes on the top, and then I'm going to get 0.033 divided by 0.10. Then I'm going to take the log of it, and then I'm going to add it to 4.74. Ultimately gives me a pH of 4.26. Because the pK here is 4.74. Plug all that in. You Hasselhoff it at that point, should be easy. 4.26, so not sure why the sig figs are off on this, but you should get A should be the answer. 4.3 is your pH. Next one. Titration curve shown below represents the titration of a weak acid with a strong base. Which point lies in the buffer region? If I connect my dots here, that's my titration curve. The buffer region on a weak acid strong base titration is represented right there. So then Roman numeral 2. If I had to find, or if I needed to find what point pH is equal to pKa, see how that's 25 is my value at equivalence? So if I went to 12.5 and I found a dot right here, I could trace it over. That would be my pH at halfway to equivalence, because pH is equal to pKa, halfway to equivalence. That's another thing you would want to be aware of as far as the test. So I hope this helps. This is the second set of questions. I'll put one more video online that has the rest of them.